Every PLC reads analog sensors, pressure transmitters, temperature probes, flow meters. They all output a 4 to 20 milliamp signal. The first question most people ask is, why 4? Why not 0? The answer is the live zero principle. A loop carrying 4 milliamps at zero process value is alive. Current is flowing. The transmitter is powered. The wiring is intact. If that current ever drops below 4 milliamps, something is wrong. Broken wire, open circuit, unpowered transmitter. The PLC can detect that condition and fault correctly instead of silently treating it as a valid zero reading. A 0 to 20 milliamp system cannot do that. 0 milliamps looks identical to a dead circuit and a real zero reading. You cannot distinguish the two. 4 to 20 milliamp was standardized precisely because live zero gives you broken wire detection for free. Every process transmitter you work with in industry will use this range. The analog module converts current to a raw integer count. The count range depends on the hardware. A Siemens S7-1200 or S7-1500 module typically uses 0 to 27,648 for the standard range. An Allen Bradley Compact Logix module typically uses 6,192 to 32,767 for 4 to 20 milliamps. 0 to 6,191 is the sub-4 milliamp underrange fault zone. Some modules normalize to 0 to 4,095 for 12-bit resolution. The exact range is in your module datasheet. What matters conceptually is this. The raw count is a dimensionless number. It represents where the signal sits between its minimum and maximum. To get a useful number, apply the scaling formula. That maps the raw count onto your process range, PSI, degrees Celsius, liters per minute. The scaling formula is a linear interpolation. Engineering units equals EU min plus a ratio times the EU span. The ratio is raw minus raw min, divided by raw max minus raw min. Multiply that by EU max minus EU min, then add EU min. That fraction in the middle is a ratio. It tells you what fraction of the way the raw count sits between its floor and ceiling. Multiply that ratio by your engineering unit span and add the minimum to offset it. The result is the process value. This formula is the same regardless of sensor type or PLC platform. Whether you are scaling a pressure transmitter, a temperature probe, a flow meter, or a level sensor, the same interpolation applies. The inputs change. The formula does not. Here is the worked example. Pressure transmitter, 4 to 20 milliamp, 0 to 100 psi, Siemens S7-1200 module, raw range 0 to 27,648. The raw count at mid-signal, halfway between 4 and 12 milliamps, is 13,824. Apply the formula. 13,824 minus 0, divided by 27,648 minus 0, is exactly 0.5. Multiply by the span. 100 minus 0 is 100. 0.5 times 100 is 50. Add the minimum. 50 plus 0 is 50.0. The scaled value is 50 psi. That is the physical midpoint of the pressure range. The raw count at the module midpoint maps exactly to 50 psi. The formula tracks linearly all the way from 4 milliamps at 0 psi to 20 milliamps at 100 psi. Now the free calculator. The 4 to 20 milliamp scaling calculator is at plcsimulationsoftware.com/tools/4 to 20 milliamp scaling calculator. It is public, no login required. Enter your raw minimum and maximum for your specific module. Enter your engineering unit minimum and maximum for your sensor range. Enter the raw count you want to convert. The calculator applies the formula and shows you the scaled engineering unit value instantly. You can also run it in reverse. Enter an engineering unit value and get the raw count that corresponds to it. This is useful when you want to test what raw value your PLC should see at a known pressure or temperature. The calculator is linked in the description below. How does the scaled value flow into ladder logic? The pattern is what I call the physics-to-boolean bridge. The analog scaling lives in a single math instruction or a dedicated scale function block. That block reads the raw count from the analog input address. It writes the result to AREAL tag, something like pressure_PSI. The ladder rungs never touch the raw count. They touch only the scaled tag. A comparison instruction then drives a Boolean bit. Greater than. If pressure underscore PSI is greater than 80 PSI, set high underscore pressure underscore alarm to true. That alarm bit is a plain Boolean. The rungs downstream that open valves, trigger alarms, or shut down equipment all use Boolean contacts. The physics lives in one block. The rungs stay clean. This separation is important because it makes the logic readable and makes the threshold values easy to find and modify. You do not want raw count comparisons scattered through your rungs. You want the scaled value in one place and the thresholds expressed in engineering units. The analog scenario track at plcsimulationsoftware.com walks you through this pattern hands-on. The analog 0-1 pressure scaling scenario gives you a running simulation with a 4 to 20 milliamp pressure transmitter. You scale the raw count to PSI using the formula, set a high pressure threshold, and wire the alarm bit. The scenario auto-grades your rung. The link goes to plcsimulationsoftware.com/scenarios/analog 0-1 pressure scaling. The full analog input examples blog post, also linked below, has worked examples for temperature and flow alongside the pressure transmitter case. To recap, 4 to 20 milliamp starts at 4 because live0 gives you broken wire detection. The raw count from your analog module maps linearly onto the signal range. The scaling formula is a linear interpolation, raw fraction times engineering unit span plus engineering unit minimum. Apply it once in a math block, store the result as a real value. Then drive Boolean threshold bits with compare instructions. Keep the rungs Boolean. The free scaling calculator is at plcsimulationsoftware.com/tools/4 to 20 milliamp scaling calculator, linked in the description. Practice the pattern in the analog scenario track, also linked below. If this cleared up the live0 question or the scaling formula, subscribe. The channel covers PLC programming from first rung to industrial controls work. See you in the next one.